Good evening, physical science guys and gals. How are you guys doing today? This is going to be our section 4 notes. So our section 4, as it says right here, is going to be chemical energy and reactions. So this is what your homework for this evening. So you want to have the sheet of paper that I gave you in class today out with you. So you want it next to the side so that you can take the notes as we go through the video. All right, so I'll see you guys in just a little bit. I'm going to go ahead and get rid of my video. All right, so that video is gone now, so let's go ahead and get started with our section 4. So first thing, the goals of this lesson is to identify the sources of energy, compare exergonic and endergonic. I know they sound like funky words, but they're not that difficult, so when we get to them, I'll make them nice and easy. And we're going to describe the effects of a catalyst, ooh, we've talked about that word, and our new word, an inhibitor. So first thing, when we have a chemical reaction, any chemical reaction, all chemical reactions are going to release or absorb energy. It just depends on what kind of reaction they are. Some reactions are going to get hot, and some reactions are going to get cold. So if they need some kind of heat, if they change the temperature at all, whether the reaction gets hotter or colder, that's still a change in our thermal energy. So our thermal energy here then, anytime we have basically a change in the temperature. We can also know a chemical reaction has taken place because we'll see light, so anything that's set on fire. We can have sound, so think of a really loud explosion like a bomb. It makes a big boom. Or if we have electricity. So chemical bonds are the source of this energy. When things actually combine together, they are storing that energy. So when a reaction gets hot, it's because the chemical bonds have added energy that when we break them, we release the heat. Light is the same way. Sometimes when we make a chemical bond get broken, light and sound can be released. So when these bonds are broken, or whether they're made, sometimes when we make bonds, we can have energy released. So just to, clue you in, anytime we make a bond, we're going to use energy. So let's say we're making a reaction and energy happens to be released. These kinds of reactions are called the exergonic. Notice the word I put here, exit. Kind of sounds very similar to exergonic. They kind of have the same EX for the beginning. That will help you to figure out which direction the energy is going. So exiting, if our energy is being released, an example of this, we have a glow stick. We crack it in half. That causes our reaction to take place. It produces light. So in this case, energy in the form of light is being released from that chemical reaction. Another example, heat packs. You ever played with the little heat packs? You crack them open. Whenever you crack them, it again activates them and it releases heat. So again, if we're giving off light, heat, or if we happen to be giving off a very loud sound, such as a rocket. Think of a rocket zooming up into the air. It produces a very loud noise and light when ignited. So all of these exergonic have things exiting, things that we can see. We can see it makes light, we can feel that it gets hotter, and we can hear that there's a very loud noise made. One specific type of exergonic reaction is one called an exothermic reaction. Look at this root word here, therm. Therm is just like thermal. So this is an exiting, oops, let me go back, exiting our thermal energy. So this particular reactions are only when the thermal energy is released. So if we look at our three examples that we have up here, which one of those three examples deals with just thermal energy being released? Ho Hopefully you said the heat packs. If you did, great. Our heat packs are activated, they release heat. Heat is our thermal energy. So, like we said before previously, sometimes energy is released, sometimes we require energy. It just depends on the kind of reaction that's taking place. So if we require energy to have our reaction go, those are called endergonic reactions. So again, I put a word here so you can associate ender with enter. So endergonic, enter. Think of it as energy needs to enter the system in order to have this reaction occur. So here we're going to use electricity, light, or use thermal energy to get a reaction to occur. So one thing that we want to look at, see if I can get my pen up here. Oops. Anytime we are dealing with adding things to our reaction, how should we write those things? Electricity, light, or heat? How did we write them before? Ooh. So on your paper, there's a question that asks you, how would we identify an endergonic reaction just by looking at the chemical equation? See if you can answer that one. So above the arrow for the reaction, we would write the word electricity or light, or we could write heat. An example, electroplating a metal. Basically what they do is they take a metal, something, aluminum, and what they do is they're going to add electricity to it, and it's going to provide the energy needed to keep the reaction or keep the two metals together. Kind of like a rust protection coating. So we're going to use electricity to keep one metal stuck to the other metal. And just like the other one with our exergonic, endergonic also has endothermic. Therm, remember, means heat, thermal energy. Endothermic reactions, when energy is needed, it's going to be thermal energy. So again, this is just a specific type of endergonic reactions. So one example of an endothermic reaction is a cold pack. So they have cold packs now that are just like hot packs. You just crack them in half, or you crack them and you shake them up a little bit, and you're mixing the chemicals. When activated, these cold packs get cold because it's going to suck the energy from the system to lower the temperature. So it's going to take the heat from those chemical bonds and it's going to use it to make its temperature get lower. Alrighty, our last slide then talks about catalysts and inhibitors. Catalyst is a word that we've seen before. So a catalyst is used to speed up a reaction that would proceed slow. Notice that it just speeds a reaction, is used to speed a reaction. It doesn't necessarily make the reaction go, because notice it says it could proceed slowly. All a catalyst does is affect the speed. If it takes us 2 hours without a catalyst, add a catalyst, it might take us 15 minutes. So all it's going to do is just speed up what would naturally happen. But, all right, but, it is not changed during the reaction. So our catalyst, again, is not changed during the reaction. It is not a reactant, and it is not a product. How would we write a catalyst in a reaction? So think about that. On your worksheet again, there's a question that goes through and asks, how do you identify in a chemical reaction if a catalyst was added? So if you forgot, look back at section 1. So this catalyst is going to remain unchanged during the reaction and can be recovered and reused. That's the key to a catalyst. We can recover it, we can take it out of the reaction, and we can actually reuse it again and again and again. All right, an inhibitor. Think of the word inhibit. Inhibit means to stop something. So here we use it to either slow down or stop a reaction. So think about a reaction you don't want to have happen. All right, I'm thinking of food. Yeah, no, hungry sometimes. Yeah, that happens. So anytime we have food, preservatives are added. The preservatives are added to slow down the spoiling process. So we're not stopping it completely because yes, eventually your food will get moldy, but we are definitely slowing it down by adding those preservatives. The preservatives themselves are an inhibitor. So two of the main inhibitors are food preservatives such as BHT and BHA. So those are two of our main inhibitors. And the last one then, neither one, a catalyst or an inhibitor, will change the amount of product made. It only is going to affect the speed of the reaction. So if we add a catalyst, it's going to make it go faster. If we add an inhibitor, it's going to make it go a lot slower. It doesn't change anything about the amount of product. Alrighty, so that was it. So tomorrow in class, we're going to be working through a worksheet that uses these ideas further. So we're going to take what we've learned here and we're going to apply them in class. So if any of this confuses you, or if after tomorrow doing the worksheet in class, if you're still confused, rewatch this video whenever you need a refresher on this section. Okay? So have a good evening, guys, and I will see you tomorrow.